Wireless fundamentals, signal-to-noise ratio, and wireless strength. By the time you're done here, you will be able to understand and analyze wireless signal-to-noise ratio and strength. Now, this slide might look familiar. That's because it comes straight from the previous nugget where we started talking about the fundamentals of wireless, and we got into the frequencies and what those are and the amplitude of the signal being the strength, and we just finished talking about received signal strength indicator, and I ran out of time and said I just don't have time to talk about the signal-to-noise ratio. And I could talk about that right here, but it's going to make a lot more sense if you understand the strength of wireless signals. So let's do that right now. Now let me remind you, the goal of all network communication, whether you're using Ethernet cable, fiber optic cable, or wireless networking, is to send zeros and ones from one point to another. When it comes to wireless networking, the way it does that is by using radio frequency. And the frequency of a radio signal represents how many cycles it completes every single second. One cycle equals 1 hertz. That's what we talked about in the last nugget. But the problem is with 1 hertz, you can't really send that much data. And that's why we talk about radio frequency in terms of kilohertz or megahertz, or in the case of wireless networking, gigahertz. For example, the common 2.4 gigahertz frequency will cycle 2.4 billion times every single second. But now let me ask you this question. What is a cycle? A cycle of what? Like a motorcycle, a bicycle? What is this cycle? And the answer is power. When you plug in a wireless access point, it starts taking the power that it's receiving from the plug or the Ethernet cable, if you're using power over Ethernet, and broadcasting that power into the air. And electricity, when it's broadcast, literally takes on a waveform. So you can think about every single time you walk by a wireless access point, you're getting shocked. And the reason that we don't see all these people twitching in business networks is because the shock is so low. The power is so low by the time it actually reaches you. As a matter of fact, most indoor WAPs transmit power somewhere between 1 and 100 milliwatts. And most of that power will be completely lost through something called free path loss. Think about it this way. Just about every indoor wireless access point has an omnidirectional antenna. That means it broadcasts the signal equally in a sphere around that wireless access point. So if you imagine your laptop sitting 100 feet away from that access point, how much of a percentage of that power do you think you're actually receiving there? Just a really small fraction, right? As a matter of fact, a good wireless signal is actually 1/1000th of a milliwatt. A really bad wireless signal is 1/10 of 1/1000th of 1 milliwatt. And what I'm trying to do as I describe this is first off, tell you just how little power is needed to send a waveform, but also to tell you the insanity that it would be if we tried to use power as our measurement for wireless signal. Imagine walking up to Sally and being like, "Hey Sally, what kind of signal are you getting on your laptop?" And she's like, let me see, 0.0005191 milliwatt? What does that mean? We don't know. And we also have to realize that power measurements are logarithmic in nature, meaning those values will exponentially grow and shrink based on the amount of power you're receiving. So let me say it this way, and I want to state it clearly. Yes, you could technically always measure your signal in terms of power because that's what's being sent into the air. But practically, you never want to. So stepping onto the scene is our good friend Alexander Graham Bell. Let's give him a good pair of glasses because I'm sure he had some. Alexander Graham Bell developed a system for measuring loss of telephone signal over a wire. And when you create systems, they actually name it after you, the Bell system. That's used to measure a 10-to-1 loss. So if my telephone signal was X strength over here and Y strength over here, and Y strength happened to be 1/10 of what it was originally, I would say there's 1 Bell of loss. Now keep in mind, the Bell system is totally relative. X could be an insane amount of power. Maybe your telephone signal is 1 billion watts. As long as by the time you got here, it is 1/10 of 1 billion watts. I guess that would be 100 million watts. You've lost 1 Bell of power. This measurement system adapts to whatever strength of power you had originally. Now, it didn't take too long for them to say, 10-to-1, that's a big move. Let's make that a fraction of it. And they created a decibel. It's actually hard for me to say that because we're so used to saying a decibel. But I enunciate my words to emphasize deci is 1/10 of a bell. It allows you to measure smaller amounts of loss. And you can use decibels for all kinds of stuff. Most of the time, if you think of decibels, people think of audio equipment. Well, they adopted the decibel yet one more time, and they called it a dBm. A decibel relative to a milliwatt. Because remember, what are we doing? We're sending power into the air, and we need to have a way of measuring loss of that power by the time it reaches our device. Thus, the common measuring system we use for wireless signals is measured in dBms, decibel relative to milliwatt. I want to show you something. I'm going to open a program called Channelizer Pro, which is a spectrum analyzer. Now, most people freak out when they see a spectrum analyzer. They're like, oh, it's super technical. Only ultra geeks know how to use this. I'm telling you, if you want to be a wireless engineer who's worth their weight in salt, you got to learn how to use a spectrum analyzer. And when you get used to it, it's actually not that bad at all. Now, my goal right now isn't to teach you how to use a spectrum analyzer. That'll come a little bit later. But I do want to give you the basics, at least as it relates to signal strength. First off, over here, you see what's known as a waterfall graph. It's just ticking down. This looks scary. This is what actually scares most people, is when they see this, they think of like alien seismic activity or something, This does not represent alien activity. It just represents signal strength over time. It's kind of measuring it and streaking it along. This has become a good common format that people have seen. Now, what I actually see right now, just by looking at this waterfall graph, is it looks like our activity increased right around, it looks like this channel 11 area of our 2.4 gigahertz spectrum. That, by the way, is what I'm monitoring right now with this guy. Right here, you see the individual channels of the 2.4 gigahertz spectrum. Now, I know we haven't talked about the channels of 2.4. That's actually going to come in the next nugget. I'm just, again, giving you a brief overview of all this. What I'm going to do is I'm going to go right here and turn on the activity to show kind of what activity is happening on this wireless spectrum right now. And then I'm going to show the maximum trace, meaning show me the maximum signal strength that you've seen on each one of these. Notice that signal strength is being measured in dBm right now. The way they scaled this for wireless is they said a value of 0 dBm is actually equal to 1 milliwatt. Now, that would be an insane amount of power for a wireless signal if you were to receive that entire milliwatt of power. That's why dBm are always in negative values. You're never going to achieve 1 milliwatt of power. So a really good wireless signal is a negative 30 dBm. And you saw I mentioned just a moment ago, a negative 30 dBm is 1/1000th of a milliwatt. Oh, that's why all of these values are negative when we're talking about dBms. And the less negative you are, if I could say it that way, the better you are. That's why I said the closer to 0 that you are, the better your signal is. The only other thing I want to mention right now is that wireless signal does not necessarily mean activity. Meaning people will look at this little jumping around and all that's going on right here and be like, wow, phew, you got a crazy busy wireless spectrum right there. And that may or may not be true. Right now, we're just not looking at it. If I wanted to, that's where I would say, show me the percentage of use. There we go. Okay, what that tells me is that channel 11 right here is pretty darn busy. Something's going on that's utilizing that bandwidth, but all of this other space over here is definitely less busy. If I were to click this utilization, actually it's already clicked down at the bottom here, this percent utilization, let me squish this up a little bit. You can see that the channel 11 area is utilized somewhere around 20-30%. That's a decent amount, and it's dropped down between my little pauses and video clips. So whatever was using that bandwidth is definitely taming itself down. Now I want you to notice something else. Do you see this pool of bubbling lava that's sitting down here at the bottom of the graph, this little red area? This section is known as your noise floor. And you notice I'm somewhere around, I'd say, negative 110 dBm for that noise floor. Think of this as murmuring on the wireless network. It's just all of these signals that are going about. They're so weak that you can't really tell them, and they're like whispers. You can't really make them out, but they're just there. It's just noise. We definitely don't want our signal to be down in that land. Now, right up top, you see our signal strength, which is actually much more powerful than the noise floor. But all this time, we've been looking at this signal strength in terms of the maximum. And let me ask you this. If you're drafting a basketball player for your team, do you want to know how many points they scored in their best game ever? Or do you want to know the average amount of points that they've scored in the game? Well, it's an easy answer. You want to see the average, right? because they could have had just a great game out of the blue. Well, it's the same with wireless signal. Right now, I'm looking at the best possible score ever, the maximum trace. I'm actually going to remove that. And let me remove all of this little jumbly signal right here. And I'm going to introduce the average trace. It's saying, you know what? We got some great wireless signals kind of shot in the dark, if you will, way up here. But on average, I'm seeing the wireless signal for channel 1 looks like around that negative 54-ish dBm. Channel 6 looks like it's around that negative 55-ish dBm. The average is a little more useful to me when I want to determine what the actual signal strength is on that network. So right now I'm going to bring this all the way back around to the beginning where I said, let's talk about signal to noise ratio. Because there are really two things that dictate the quality of your wireless signal. One is the signal strength, which I'm going to show you a great table on in just a moment. And the other is your signal to noise ratio, as in how strong is your signal compared to the amount of noise that you're getting in your environment. The formula to find this is simple. You take your signal strength and subtract your noise floor. Now you remember our noise floor just a moment ago on that analyzer was a negative 110 dBm. And you might remember when you'd subtract a negative number from your old math days that it's actually adding. I'm trying to keep as much math out of this as we can because you can get deep. I'll just tell you the easiest way to calculate your signal to noise ratio is to get all the negative values out of it and just take your noise floor, 110, and subtract your signal strength, which we saw the average on most of those channels was about 55. Ironically, that tells us that our signal to noise ratio in this case is actually 55 dB. Notice first of all that it's not a negative value, nor is it a value of dBm, because we're not really referencing power in this case. We're just saying the difference between the signal and the noise is 55 dB. And I'll give you your rule of thumb right now. You want to write this down. A high quality signal needs to have at least a 25 dB signal to noise ratio or better. So in our case, a 55 dB signal to noise ratio is great. The second thing I want to give you is your signal strength. We know that our signal to noise ratio was 55 dB, and we know that our signal strength for most of those networks was negative 55 dBm. But where does that rate? This is a great tool to tell you just about how good your signal strengths are. You can see right at the top is negative 30 dBm. It says the maximum achievable signal strength. The client can only be a few feet from the access point to achieve this, and this is not typical nor desirable in the real world. You're too loud in that case. Then you see a giant gap between negative 30 and negative 67, which is the minimum signal strength for applications that require very reliable, timely packet delivery. Then all of a sudden, it seems like we reach this, negative 3 less, and it's the minimum signal strength for any packet delivery at all that you want to be reliable. Once you go beyond negative 70, you're in the weeds. It seems like just a drastic difference between those two, doesn't it? Well, take a look over here. You remember I mentioned that power is a logarithmic function, and they adapted that over here to dBm. So when you're looking at a loss of negative 3 dB, that's literally half of the signal strength. So negative 70 compared to negative 67 is half the signal strength. And then that tells you what a drastic difference there is between a negative 30 and a negative 67. I would suggest taking a screenshot of these two tables right here and printing them out and literally taping it on the laptop that you plan to use to discover wireless networks and support them and so on. I wish I had a picture of my laptop that I used when I first started doing wireless site surveys. These exact things are printed out on there and they're all tattered and beat up from being thrown in and out of my bag, but there they stay, at least until you can cement these values in your head to where you can tell the relative strength of a wireless network just by looking at the number. And one more thing as I see this "you will" statement hit me square between the eyes. You might be thinking, okay, do I really need to get a spectrum analyzer to be able to understand and analyze the signal to noise ratio and wireless strength? I mean, I pulled up the wireless analyzer on my laptop that, uses the built-in network card, and it looks like I can get a pretty good rating of what's going on. And I would agree with you. This does give you the wireless strength of the networks that are using the 2.4 gigahertz spectrum in this case. But the problem is this: your wireless card is geared to only see wireless networks. That's what it's built to do. Whereas a spectrum analyzer sees everything in that wireless space. Notice right here when I click on this signatures tab, they're saying, hey, you know what? You might see a pattern that looks like this. Hang on, let me Let me turn off the utilization and turn on this little outline right here. This is where it's trying to put patterns together of what's using it. It's saying you might see a pattern that looks like this right here, where it's constantly peaking up. That would be a cordless phone. Oh, you might see a pattern that looks like this. That might be a Bluetooth interference. You see, as I'm scrolling down here, there's Logitech headsets, Motorola canopies, Nortec videos as I'm going down this list. Your wireless card will not see any of these things. These are non-wireless network signals that only a spectrum analyzer can see. And I guarantee that you're going to run into those weird situations where the wireless signal seems strong enough and things just aren't working well. Without a spectrum analyzer at that point, you're just doing guesswork, which is actually what most network engineers today do. Now, I told you at the beginning of this, you will understand and analyze wireless signal-to-noise ratio and strength. And I've got to say, I'm so excited to where we actually get into our practical deployment where I can say, so here's what I want you to do to prove it. It's kind of awkward to me to be in the primer material because right now I'm just giving you some concepts that I want you to grasp before we get into the practical implementation later on in this series. For now, I hope this has been informative for you, and I'd like to thank you for viewing.